Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss further on the Bernoulli's equation and we will revisit the issue of compressibility of a fluid. So, we will look at Bernoulli's equation and its applications and further compressibility. You may recall last time we had derived Bernoulli's equation and we should recall about the assumptions that were involved while we derived it. So, you may have in mind that we were dealing with irrotational incompressible inviscid flow devoid of body forces, which gave us this equation that pressure plus half rho v square is equal to constant, and then we discussed about the issue of whether it is a rotational or irrotational flow. Accordingly, the constant will hold along a streamline or across any two arbitrary points in the flow field. Now, while we derived the Bernoulli's equation, we made use of the momentum equation. And thereby, this is essentially a statement of momentum conservation for inviscid incompressible flow with no body forces. And as we said that rotationality or irrotationality will affect how you apply this equation, whether it is along 2 points on a streamline or arbitrarily any 2 points in the flow field. So, for rotational flow fields it should be along a streamline, for irrotational flow field it could be 2 arbitrary points in the flow field. Now, additionally when we look at this term half rho v square, if you look carefully, this is nothing but the kinetic energy of the fluid per unit volume. Therefore, it is talking about the mechanical energy of a fluid element in incompressible flow. That means, it has to do with mechanical energy conservation as well. So, an energy conservation comes into the picture here within the given assumptions. So, if that is the case, how do we interpret it? We interpret it this way, that the pressure forces have acted on the fluid element and it has caused a change in the kinetic energy of the flow. This is how we would like to interpret it. Thereby, this gives you the energy conservation point of the picture. Therefore, this equation can be interpreted from both angles. However, if we are not looking at the energy conservation point of view, even then purely from the momentum equation point of view, we could have derived it. That means, the energy equation is essentially redundant. For the kind of flow field that we are dealing with. So, in inviscid incompressible flow, just by using the continuity equation and momentum conservation equation, you could work out the variation of pressure and velocity through the flow field. Anyway, because it is assumed to be incompressible, that means the density is not changing with change in pressure. So, density is a constant. it can at most be a function of temperature that we have discussed earlier. Therefore, we realize that in inviscid incompressible flow field only continuity equation and momentum equation are of importance. However, we may recall an earlier discussion when we were deriving the conservation equations and we came across the energy equation derivation, that when it comes to a high speed flow, then when you look at the kinetic energy per unit mass of a moving fluid element, which is V square by 2, this becomes very large, and it becomes so large that this starts playing a very dominant role in affecting the flow properties. And therefore, all the conservation equations feel the presence of a large V square by 2 term. Consequently, we have to invoke the concepts of thermodynamics, so that we can look at it from the energy and entropy perspective. Thereby, the first law comes up when we talk about energy conservation. This is the perspective, and that is where we brought in the concept of compressibility. And this term del V del P is a partial derivative keeping either temperature constant or entropy constant. When we keep the temperature constant, what we get is isothermal compressibility, and when we keep the entropy constant, we have isentropic compressibility. So, when the gas is compressed, work is being done on it, its temperature is going to increase. So, to keep it isothermal, we have to extract heat from the gas in order to maintain a constant temperature. While in an isentropic compression, there are no irreversibilities and we allow the temperature to change. Everything is reversible in this case. Now, if you look at this definition of compressibility, what it essentially means is it is a fractional change in the volume of the fluid element per unit change in pressure. So, we notice that if we have a positive value of dP, that means the pressure is rising, that would lead to compression of the gas, and therefore, you would say that the dV would be negative, and consequently, the tau will be a positive term, because you have a negative term here. By definition, specific volume is 1 by density, because you are taking unit mass, and if you take a product of that, then it gives you say rho times volume equal to 1, and then if you take a differential of that, then what you get? You get V d rho plus rho dV equal to 0. From this relation, we can obtain dV d rho is equal to minus V by rho, and dV dP is equal to dV d rho into d rho by dP which is minus V by rho times d rho dP. Now, going back to the definition of tau, that means you will have which will come out to be 1 by rho d rho dP, that is what it will work out to be. So, finally, what do we have? We had written down this relation straight away without deriving last time. So, here we show the formal derivation. So, whenever the fluid experiences a change in pressure, that means you are applying an additional pressure which could be expressed by dP, the corresponding change in density is given by this relation where the compressibility comes in. Now, compressibility of gases is way larger than that of liquids, and therefore, gases have a large value of tau here, and even the smallest of changes in pressures could actually lead to conceivable changes in density. When pressure changes are high, density changes are obviously going to be high, and high speed flows are generally accompanied by large pressure gradients, and therefore, the consequent effect that there would be massive changes in density in the medium. So, thereby we consider them to be compressible flows, and here by high speed flows we are meaning flow of gases including air and other gases or gas mixtures. Going back to the two definitions of compressibility that we just discussed, the isothermal compressibility for constant T, if you want to take the expression forward by invoking the ideal gas equation of state. How can we take it forward? We can derive an expression for del V del P for constant T. So, for constant T, the right hand side will become a constant, let us define it as K, and then we will have del V del P So, this will come out to be minus V by P. So, if you substitute it back, therefore, rather we should put it this way, that there should be a multiplied by minus 1 by P, which will give you 1 by P, 1 by pressure. On the other hand, when you are trying to work out the compressibility for an isentropic case, then it has to be for constant entropy, and then you have to invoke the state relation for isentropic process for an ideal gas, and if you have that, then you can express V to the power of gamma as K by P, and therefore, V is K by P to the power of 1 by gamma. So, gamma is the ratio of Cp by Cv, the ratio of specific heats. Now, when you work out the del V del P, for constant entropy, what does it work out to be? So, when you take the derivative, this derivative will come out to be minus 1 by gamma p to the power of minus 1 by gamma minus 1. So, finally, you can rearrange it into k by p whole to the power of 1 by gamma into 1 by gamma p, and that can be further represented as v by gamma p. So, finally, what you have is tau. When you substitute this into the tau equation, what you get is 1 by gamma p. So, in the earlier case, for isothermal case, it was 1 by p, while here it is 1 by gamma p. Now, what does this mean? Since gamma is going to be greater than 1, we have the situation that isothermal compressibility is always higher than isentropic compressibility. That means, if you maintain a gas at constant temperature while you compress it, there will be larger density changes. Okay. So, whether isothermal or isentropic, if the pressures are conceivable, then there will be significant changes in density, and therefore, what finally matters is the density change, and a few percent change typically restricted to about 1 or 2% may be ignored, and then we can consider that kind of a situation as incompressible. But typically, when the density change becomes about 5% or so, you can start considering the fluid to be behaving as a compressible one. Finally, we recall that very important expression which gives us the density change in terms of the pressure change and the compressibility. Typical values of say isothermal values of compressibility can be given as 10 raised to the power of minus 5 meter square per Newton for air at 1 atm and 5 into 10 to the power of minus 10 meter square per Newton for water at 1 atm. Okay. So, you can figure out that air is far more compressible than water. So, we wanted to revisit the concept again, because we are interested in the change in density with change in pressure, and that is what distinguishes the compressible flow from an incompressible one for us. There are more ways to define and distinguish compressible and incompressible flows, which we will discuss in due course. Having said that, we would like to go back to Bernoulli's equation again and look at a few applications of the equation. So, let us say we are looking at an uniform flow moving past an airfoil, and the flow is coming in at about 45 meters per second. The free stream pressure is 10 raised to the power of 5 Newton per meter square. The density at free stream is 1.2 kg per meter cubed, and we record a pressure of 0.9 into 10 to the power of 5 Newton per meter square on the airfoil. So, considering the flow to be inviscid and incompressible, we would like to find out what is the local velocity at this point, where the pressure has become 0.9, that is about 90% of what it is in the free stream. So, obviously, we invoke the Bernoulli's equation and we try to apply it between the two regions by taking this as the point on the airfoil. Remember that because we are considering inviscid flow, the velocity on the airfoil surface can slip, and what you have in the free stream. And if we consider further that this flow is devoid of any rotational effects, that is, it is irrotational, then you can apply it arbitrarily between any point in the free stream and that point. Otherwise, we apply it along a streamline. So, once you do this, you can rearrange the terms and you can express the velocity in terms of the other quantities in this way, and because it is incompressible, there would be no significant density changes, and therefore, we consider it to be constant. And then once you plug in those values here, you will see that the velocity comes out to be 136.7 meters at that point, which is significantly larger than this. That means, the shape of the airfoil is such that the flow has accelerated considerably before it reached that point. Similar acceleration may be produced if you take this flow through an internal passage. This was an external flow past the airfoil. Similarly, you can have internal flow through a duct. We would call this as a variable cross section or better to call it as converging diverging duct. A converging diverging duct. Why so? Because this is the cross sectional view of the duct, and let us say we assume it to be a two dimensional one. That means, along the depth there is no change in geometry. So, you can imagine that at this section the cross sectional area is what? It is this height into unit depth, that will be the cross section. Naturally, if you go to another section, there the height would be different, and when you multiply it with unit depth, the cross sectional area also reduces. Again it increases, and that becomes much larger than this cross section. So, that way point to point the cross sectional area changes. So, if you locate your x axis origin here, then the area, the cross sectional area is basically a function of x. Now, you can define the different flow field quantities like velocity, pressure, say density at this station, and you can locate it at the other end of the duct. And of course, we continue to assume that the flow is incompressible, therefore, we will consider it to be invariant with pressure change. And then if you look at how these values would connect with each other, it is very important to recall some of the conservation equations that we have learnt about. Let us say we recall our mass conservation equation. So, the mass conservation equation was derived in a general form which can include unsteadiness in the flow field. Now, here we will assume the flow to be steady and therefore, this term goes to 0. We have the flux term, which if you carefully apply on this flow, you can define a control volume which just follows the internal surface of the passage, and you are trying to figure out how the fluxes have occurred across the boundaries. Now, we notice that along these curved surfaces, everywhere if you look at it, the surface normal points out and the velocity is tangential. Therefore, they are orthogonal and hence a dot product would yield a 0. However, the dot products would not yield zeros here. So, let us perform the dot products at the two planes, let us say 1 and 2, which we can call as inflow and outflow of that converging diverging duct. So, we say that this portion is the converging one and this portion is the diverging one. So, in the converging part, the area is reducing as you move along the length of the duct. In the diverging part, the area is increasing as you move along the duct. So, in the inflow section, what happens is you have a rho V 1 I. So, V 1 I expresses the velocity in a vectorial sense and minus I A 1 is a surface vector, because at the inflow the velocity points inside, the surface vector points out, and therefore, since it is pointing towards the negative x direction, you have a minus I associated with it. While in the outflow, so this is station 1, in the outflow the velocity points out, so does the surface vector. So, we are just showing the unit vector which points in that direction. So, if you represent these vectors using the unit vector, that is how they look. So, this is how it works out, and that should be equal to 0. What it finally means is A 1 V 1 is equal to A 2 V 2. So, continuity equation basically boils down to this equation. Now, if you were interested to find out how pressure changes, because as you can understand that pressure acts normal to this surface at any location and it points into the flow. So, if somebody is interested to work out pressure and let us say we have moved an x distance from the origin. So, at that x location, how do you indicate pressure? You can indicate it this way, that you start from the inflow plane, where by Bernoulli's equation the total sum of the static and dynamic pressure is this, and then at an arbitrary section, what does it work out? It works out like this, and then you try to write that velocity at that section in a way like this, because we have come to know that continuity equation relates the product of areas and velocities like this. So, if you look at this, you have the x location incorporated and you can also mention this as P x because the pressure is changing along the location. So, P x will finally turn out to be P 1 plus half rho V 1 square minus half rho A 1 V 1 by A x whole square. So, this is how pressure would change as you move along the duct. Again remember that we have considered the flow to be inviscid, incompressible and devoid of body forces, and that is why we could apply the Bernoulli's equation. So, we have looked at the issue of compressibility, and we have also discussed about some aspect of Bernoulli's equation through applications. So, in this lecture we discussed about further applications of Bernoulli's equation, and since we were dealing with incompressible inviscid flows and which could be both irrotational and rotational in the context of Bernoulli's equation, we once again discussed about compressibility of a fluid in further detail. Thank you.